Our next speaker will be Alexander Kasprzyk.
Oh, yeah.
Alexander. Oh, hello.
Here we are. Okay. Hi, everyone.
Hello.
So let me try share. Okay. Good.
Okay, so we welcome Alexander Kasprzyk from the University of Nottingham, and he's going to tell us about Fano varieties and mirror symmetry.
Okay. Well, thanks very much for the invitation, and thanks to all the speakers so far. I've really enjoyed the talks that I've been able to attend. It's been good fun. I'm afraid I took Yang's advice that this should be to a general audience perhaps more seriously than I should have done. So I'm afraid I'm going to bore the audience here because this will all be stuff that you know perfectly well. But anyway, let's see how it goes. I also need to offer another apology, which is the title of my talk differs from the title I gave you. The content is the same, I just couldn't remember the title that I gave. Okay. All right, so what I want to talk to you about today is a new sort of attempt to classify Fano varieties, important varieties in algebraic geometry, using techniques from mirror symmetry. But it's more than just mirror symmetry. It becomes techniques in combinatorics and ultimately using big data, using massive parallel computations. And then in the conclusion, machine learning and techniques from data science make an appearance. Okay. So all of this work is joint with many people, but some names that I really feel I need to mention are Tom Coates, Horatio Corte, Sergei Galkin, and also other people, Vasily Golishev, Thomas Prince, Elena Kalashnikov, and my just finished postdoc, Giuseppe Piton, who did such wonderful work with the machine learning side of things that we'll come to at the end. Okay. So I mean, roughly speaking, and I'm sure I'm not saying anything that is going to surprise anybody, algebraic geometry is the study of shapes in space, okay, up to some form of equivalence. Okay, and when you get started with algebraic geometry, probably the first thing you do is you study manifolds, smooth varieties, and you quickly learn that the appropriate thing to do is to partition manifolds by their curvature. And so manifolds with positive curvature are called Fano varieties. Manifolds with zero curvature are called labials. And manifolds with negative curvature, these are called general type. Okay. And the wonderful thing is that at this end, Fano varieties, Fano manifolds, we know that in fact there's finitely many of them in each dimension. Okay. And at this end, general type, we know that there's infinitely many of them in each dimension. And the mystery still is in the middle. What happens with labials? Are there finitely many in each dimension? Are there infinitely many in each dimension? I think nobody really knows. Okay. And a wonderful construction is to take a slice through a Fano manifold, and this will give you a labial, and then you can take another slice and get yourself something of general type. So you can move from this end of the picture down to this end of the picture through slicing, but of course you're not going to get everything this way. Okay. So Fano varieties are very important, and there's finitely many of them in each dimension, and you can't help but wonder what their classification is. If there's finitely many, let's list them all. Okay. And beyond just it's a mountain, let's climb it, they're also incredibly important in birational geometry in the minimal model program. So minimal model program is a technique for taking a general algebraic variety and successively simplifying it, and in a way that can be made precise, the end result is a Fano varieties. So, you know, these are important objects of study. They're in some sense the atomic pieces of geometry. Okay. So they're so important. Let's find out with many of them, what's their classification? Dimension 1. So I don't know who to attribute this to, some ancient Greek for sure. There's exactly one Fano manifold in one dimension, which is projective space, the projective line. Okay. And well, you know, in the interest of explaining this to maybe people who aren't familiar with this, you know, think of this as the set of lines for the origin. Okay. And if you think of it like that, then you'll see quickly that this corresponds to a copy of the complex line union this point at infinity. Okay, so there's no mystery here. This is a very tame, very nice manifold. What about 2 dimensions? Well, here the work was done by the Italian geometer Del Pezzo in the 1880s. And so for this reason, we call these the Del Pezzo surfaces. And there are exactly 10 of them. Okay, so there are 10 smooth Del Pezzo surfaces. There's P2, the 2-dimensional analog of projective space, the projective line. Then there's a product, P1 cross P1. And then finally, you can do what we call blowing up. So you take P2 and you blow up in at most 8 points in general position. Okay. So blowing up is just a very natural construction in algebraic geometry. You can think of it as inserting a copy of the P1. I won't go into it in any detail, but it's a very systematic construction. Okay, and yeah, drawn a little picture here of 2 of these Del Pezzo surfaces. P2, it's exactly analogous to P1. It's just a set of lines in free space. And so just like when you're thinking about how you could project the lines onto a copy of C1, for P2, you can think of this as a copy of C2 union a copy of P1. Okay. And for P1 cross P1, I've tried here to sketch a nice way of thinking about this. So each of these red lines is supposed to be one copy of P1, and each of these green lines is supposed to be another copy of P1. And you can embed this naturally in P3, 3-dimensional projective space, and you end up with this ruled surface. Okay. So this is a really quite important construction in the real world. When you see cooling towers are essentially ruled surfaces. They're constructed exactly this way. The rules, as it were, are pieces of wood that are used, and the concrete gets poured in, and you end up with this rather familiar shape. Okay. These are really natural and important geometric objects. All right. Well, what about in 3 dimensions? So in 3 dimensions, there was a lot of work done in the 1930s by Fano. And because of this, we call them Fano varieties. And then there was a brief interlude. And then in the 1980s, work by Mori and Mackay finished the classification. Well, they finished it modulo 1 case, which they missed, which they later found in the early 2000s. And it turns out that there's 105 Fano manifolds in 3 dimensions. This was incredible work, and it was part of the body of work that won Murray the Fields Medal. And very recently, Kosher Berker has also won the Fields Medal for his work on Fano varieties. You know, these are fundamental problems in geometry that attract some really excellent people. Well, I'm not going to list all 105 cases. I've listed some very easy ones here, but you know, they get progressively more and more convoluted. What I will say is, often in maths, once you've seen how to do something, it becomes a lot easier to do later. But the classification of Mori and Mackay is still very technical. It's still very difficult. It's not really become easier over time. And what about higher dimensions? Nobody knows. We've had 30, 40 years of intense study. People were, of course, very excited at the beginning. They thought the techniques developed by Mori and Mackay would generalize nicely, but in fact, it turns out there's a sort of dimension gap. As dimension 3 is the sweet spot where Mori and Mackay's techniques work perfectly. But as you begin to increase the dimension, there's a little gap in the classification that grows bigger and bigger and bigger. Okay, so although we know a significant part of the 4-dimensional classification. We don't know all of it. And kind of the interesting piece is the bit that's missing, unfortunately. And then the situation just gets worse and worse as we go up the dimensions. So there's many wonderful ideas coming out of modern birational geometry about how you can do these classifications. They still stimulate a huge amount of important research that's led to some really great stuff. It kind of doesn't matter if we come up with the classification or not, just because it drives so much fundamental research. Okay. Anyway, about 10 years ago, I think, Tom Coates, Horatio Corti, Sergei Galkin, Vasily Golyshev, and myself, we wondered if techniques from mirror symmetry could help us with the classification of Fano manifolds. So to put this into context, mirror symmetry has been incredibly useful understanding Calabi-Yau varieties. It's really exposed their geometric structure in ways that I think people just didn't even guess was there beforehand. The intuition that's coming from physics is, really driving mathematical results in a way that's astonishing to see. We thought, well, because of this slicing argument, we can move from Fano to Calabi-Yau. We can actually borrow many of the ideas that that have been developed in mirror symmetry and apply them to Fano manifolds. Now, unfortunately, to tell you this story, I have to introduce something that's a little grotesque. And I'm not going to go into it in any detail whatsoever. And it's almost not important that you understand the math behind it. But I do want to tell you what the two sides of the mirror are. Okay. So one side of the mirror is a Fano manifold. The other side of the mirror is, I need to introduce Gromov-Witten theory. So Gromov-Witten theory gives us a very detailed, subtle technical tool that lets us begin to understand the structure of Fano varieties. And what we're particularly interested in is something called the quantum period. So the quantum period is a generating function. And what it's doing is the coefficients counting the number of curves of degree k that lie on our Fano variety, on our Fano manifold. Of course, there's a wrinkle here. It's not quite that straightforward. It's really counting curves with a particular complex structure. It's not so important. Why would you do this? Well, for a long time now, geometers have understood that if you want to understand higher dimensional varieties, one of the best ways to get to grips with them is to understand the structure of curves that lie on those varieties. So this is a very natural thing to study. Okay, and in fact, it's expected, though it's certainly not a theorem, that each Fano manifold has a unique quantum period, a unique set of these coefficients ck. And in fact, given these coefficients ck, we can go backwards and we can reconstruct the Fano variety. So if there was some magical way where we could easily construct the coefficients ck that correspond to Fano manifolds, we could imagine that that's a way of classifying Fano manifolds. And this is exactly what mirror symmetry is doing for us. Okay, so now I need to introduce the main character in this talk, and this is Laurent polynomials. So there's nothing scary about Laurent polynomials. Associated to a Laurent polynomial is what we call the classical period, given by this integral. The important thing about the classical period is it has a very beautiful Taylor expansion. And the coefficients in this Taylor expansion are very easy to calculate. You simply take the kth power of f, you look at the constant term, and that's your coefficient. Okay, so given a Laurent polynomial, it's incredibly easy to write down its classical period. And we say that f is meridual to x if the classical period agrees with the quantum period. Okay. So, on the one side, we've got something that anyone in high school can calculate. On the other side, we've got something that's incredibly technical and difficult to calculate. Any particular x that you give me, I may or may not be able to do the calculation. It's really subtle and it's really difficult. And so what our hope is that somehow we can characterize those Laurent polynomials that are mirror dual to Fano manifolds. Okay. And if we can do that, if we can classify those Laurent polynomials, we could think of that as being equivalent to classifying Fano manifolds. Okay. So let me do a very quick example to try and ground us a little bit. So I'm just going to take P2. So P2 is a very beautiful, very natural Fano manifold, and so there are well-established techniques by Giventhal and Horvath that lets us calculate its quantum period. And I mean, I'm not going to go into this, but you can look this up. There's just a formula you apply, and you'll get this as the quantum period. So the quantum period is 1 plus 6t to the 3 plus 90t to the 6 plus 1680t to the 9 plus ... And there's a lot of geometry encoded in here, as you might expect. So the powers of t that are occurring are all multiples of 3. It's no coincidence because P2 has Fano index 3. Okay, if you look at this fraction here, what we're seeing downstairs is k factorial 3 times. And again, that's not really a coincidence. It's because P2 is P1, 1, 1. And it's these 3 1s that you see here that are sitting downstairs. And it's the sum of these 3 1s, which is equal to 3, which is the Fano index, which you're seeing upstairs. So there's a lot of geometry encoded in this, and hopefully that gives you a sort of idea as to how it's sort of realistic to expect that you can recover the Fano variety from this data. Okay. But this is a very special, very easy case. In general, if you give me a general Fano manifold, I just doubt I'd be able to calculate its quantum period. Okay. Out of nowhere now, let me just give you this Laurent polynomial. F is equal to x plus y plus 1 over xy. Okay. A little bit of combinatorics, you can go away and you can figure out what its period sequence is, the coefficient of the constant term, and you'll see that it only has a constant term when we take a power of f that's divisible by 3. And in those cases, we end up with this multinomial expression, 3k choose k, k, k. Okay, which of course is exactly the same thing as the quantum period we constructed for P2. So if you could have magically somehow known to look at this Laurent polynomial, what you would have done is you'd have been able to construct a mirror for P2. Why did we look at this Laurent polynomial? Well, it's actually not so surprising in retrospect. So if we take the Newton polytope of the Laurent polynomial, so x, y, and 1 over xy, I get this triangle sitting in 2-dimensional space, in a 2-dimensional lattice. Okay, and then what I'm going to do is I'm going to pass from this polytope to a combinatorial construction, which is called the spanning fan of the polytope. So I don't know if you can see it so well on your screen, but here is my Newton polygon, my triangle. And what I've done is I've taken the cones over each of the faces of this polytope. So over each of the edges, I've got a 2-dimensional cone, 1, 2, 3. And over each of the vertices, I've got a 1-dimensional cone, a ray. Okay, and if you've ever studied toric geometry, what you'd recognize is this is a fan. Okay, and it defines a toric variety. Essentially, what this is doing is it's describing an atlas. It's telling us how, well, each of these top-dimensional cones is corresponding to a copy of C2, and we've got 3 copies of C2. And the structure of this fan, the way the cones meet the rays, this is telling us how to glue together my 3 charts of C2. Okay. And if I put coordinates and everything in one chart, I have that my x coordinate is 1, 0, in one chart my y coordinate is non-zero, in one chart my z coordinate is 1, 0. And so sitting here in the middle, I have a chart where x is non-zero, y is non-zero, Z is non-zero. In other words, sitting here in the middle, I have the algebraic torus, and it's the algebraic torus that gives these varieties their name, toric varieties. Toric varieties is very special in the world of algebraic varieties, but when you do have a toric variety, they come equipped with this beautiful combinatorial description. All right, so let's just carry on. Yeah, in fact, it's not just any toric variety. What I've got is a copy of P2 as a toric variety. So maybe it's no surprise that when I started with that Laurent polynomial, I ended up with the period sequence for P2, because in fact, secretly, I had a copy of P2. It was good. All right, so let's look at dimension 2. Well, if you remember, I said there were 10 Delpezzo surfaces, 10 smooth Delpezzo surfaces. And in fact, only 5 of these are toric varieties. So 5 of them are special. They have this dense torus sitting inside them. And what are they? Well, it's P2, it's P1 cross P1, and then it's the blow up in 1, 2, 3 points. Okay, so these are my 5 toric Delpezzo surfaces. And in each case, what I've done is I've drawn the combinatorial data that describes them. And for each of these polytopes, I just assign a Laurent polynomial in the obvious way. Okay, so here, for example, all I'm going to do is I'm going to assign the coefficients 1, 1, 1, 1 to the 4 monomials that represent the vertices. This gives me this Laurent polynomial. And in every case, the Laurent polynomial I construct in this way is a mirror for the Delpezzo surface. So what about the 5 non-toric Delpezzo surfaces? Do they have mirrors? Well, yes, they do. Okay, they all have mirrors, but now the corresponding toric variety that we extract from the mirror is not equal to the Delpezzo surface. It can't be because the Delpezzo surface isn't toric. Okay, and in fact, we have a theorem. What's going on is that if F is a mirror to a Fano manifold, this is true in all dimensions. So if we've got a mirror to a Fano manifold, then the corresponding toric variety that we construct, we pass to the Newton polytope and the spanning fan. The spanning fan is a toric variety. Well, this is QG deformation equivalent to X. Okay, not equal to X, it's QG deformation equivalent to X. What's QG deformation? Well, it's a particular type of deformation of the variety that preserves the properties of the curvature that we're interested in. So it preserves many of the numerical properties that we can obtain from the curvature. But in particular, it preserves the Gromov-Witten invariance. So the period sequence is preserved under these QG deformations. So they were studied extensively by Koller and Shepard-Barron in the case of surfaces. And this is the notion of equality or of equivalence that we just have to accept if we're going to play this game. And moving to something that's QG deformation equivalent does come at a cost. Remember, X, by definition, is supposed to be a Fano manifold, but the resulting toric variety that we may end up considering can certainly become singular. So that's bad news, because it's definitely better to work with something that's smooth than to work with something that's singular. But this is compensated for by the fact that we have a beautiful combinatorial structure, because these are toric varieties. Toric varieties are characterized by having this fan structure. So we've got this rich combinatorial theory that we can start to work with. And this completely makes up for the fact that we've now introduced some singularities. Okay. So let me show you a little example. So let's take the first Delpezzo surface that's not toric. So this is the blow-up of P2 in 4 points. And I mean, of course, I can't really justify anything that's on this page to you, but what I'm going to say is a mirror is given by this Laurent polynomial. And if you go through the motions, well, we've got this Newton polytope. And this corresponds to the fan that we see here. And if you sort of knew the combinatorics of toric geometry, what you'd see is this cone and this cone are very special. Why are they special? Because the two generators here for the cone don't generate the lattice that the cone lives in. So here, this and this is actually a basis for Z2. And this is a basis for Z2, etc. But this and also this and this, they're clearly not a basis for Z2. And under the toric dictionary, what this means is that my corresponding toric variety has got two singular charts. Okay. And we've got, in fact, these are what we call a half 1-1 singularities. So they're actually very sort of easy singularities to draw. If I took this cone just here at the origin, what you see is a nice, simple, straightforward picture of what a half 1-1 singularity looks like. They're not particularly bad singularities. It's actually, you can never get particularly bad singularities when working with toric varieties. Okay. But anyway, this is definitely singular. It's got two of these singular points in it. But nevertheless, it is a toric, it's a QG degeneration or deformation of this del Petzl surface to blow up in 4 points of P2. It comes with a mirror. And notice, it's interesting now, I've drawn the coefficients for the mirror on the Newton polytope. And what we're seeing is 1, 1, 1, 1 at the vertices like before. But now these points that corresponded to the singularities, we've put coefficients 2 on. In fact, this is a recipe that generalizes really quite well. We end up seeing binomial coefficients along the edges of our Newton polytopes. Okay. So, big theorem. It turns out that there exists a mirror Laurent polynomial for every Fano manifold in dimensions 1, 2, and 3. So this was a result by Coates, Corti, Galkin, and myself in 2016. So it's not quite equivalent to recovering Mori and Mukai's classification. We do have to use their classification. So I'm going to come clean now. We have to use their classification because we don't know when we found everything. So we have ideas about how to develop the theory so that we will know when we found everything. But at the moment, we can construct Laurent mirrors to Fano manifolds. We can do this systematically. Unfortunately, we don't know when to stop. Okay, so this is sort of the big hole in what we can do at the moment. But even so, you know, it reduces the incredibly complicated and subtle geometric arguments of Mori and Mukai to a sort of almost brute force, very primitive combinatorial search that's systematic and will find everything. Okay, brilliant. So what can we do in higher dimensions? Well, the wonderful thing about what I've described to you is it just doesn't depend on the dimension. My pictures have been in 2 dimensions, but that means nothing. This works in all dimensions. And so what we can do is we can systematically begin to explore higher dimensions. What happens in dimension 4? So in dimension 4, there's 3 papers that have come out. Coates, Galkin, myself, and Andrew Strangeway, Ilana Kalashnikov, and also Thomas Prince. And in these papers, we've taken these ideas and we've constructed mirrors for more than 700 previously unknown Fano manifolds in dimension 4. So you're going to ask me, you know, are there many more of them, or is that it? You know, I can't really answer that question, but what I can say is we're not finding any more of them so easily. I'm sure there's still a few more out there. In fact, I'm certain there's still a few more out there, but it's probably the right ballpark. Okay, so there's probably thousands of 4-dimensional Fano manifolds rather than tens of thousands of 4-dimensional Fano manifolds. So you can see this technique really does work. I just want to say one more thing before we slightly change topic. So when you start working in higher dimensions, what you quickly realize is you're not really working in the right category of geometric objects. This isn't really a construction about Fano manifolds. It's actually about terminal Fano varieties. Now, you might look at me now and say, well, this is a terrible bait and switch. convinced me at the beginning that we wanted to study Fano manifolds, and now you're saying we're looking at something else entirely. It's actually better, okay? If you do birational geometry, terminal Fano varieties are kind of like the natural family of varieties that you should work with. It's not really all that natural to be working with smooth varieties, with manifolds, but it is natural to be working with things that have terminal singularities. Terminal singularities are not bad singularities. They're about as nice as singularities can get. So actually, this is really quite an important realization. It's taken something that felt natural in the world of combinatorics, but felt unnatural in the world of geometry, and suddenly realized that, no, we just slightly misinterpreted the combinatorial picture. In fact, what's natural in the world of combinatorics is also natural in the world of geometry. And so these classification techniques actually give us a way of classifying not Fano manifolds, but Fano varieties with terminal singularities. So this is significantly more interesting from the point of view of geometry. I also want to just take a moment to say that the advantage of these techniques is they're amenable to large-scale calculations, okay? The theory is sort of in place or being developed, and whilst it's being developed, you can just go away, you can start systematically creating these conjectural classifications of your Fano varieties and produce really quite large data sets where you know that everything that's in them is a Fano variety, okay? Unique up to QG deformation. What you don't know is completeness. And so you can take these large data sets and you can start to study them. And what's the best way of studying large data sets? Well, the best way is to find someone who knows some data science and some machine learning and get them excited. And so here, my former postdoc, Giuseppe Piton, he did some incredible work. And this is where it gets really exciting, because what he's found through his work analyzing these huge data sets is incredible. I mean, it's absolutely incredible. He's found previously completely unsuspected structure amongst these classifications. So let me try and explain what I mean by that. There's a big picture here, you know, knowledge about Fano varieties and so on. And this big picture says, yes, we expect certain things to hold. We're not going to be surprised if there's some relations that are there, et cetera, et cetera. But what he's found is it's not just these relations exist, but boy, these relations don't just exist, but they're there in completely natural ways. And it's incredible. And based on his work, you know, we've got decades of theoretical research ahead of us to actually prove what his data science techniques have exposed. So I'm just going to finish by quickly showing you some examples. So this is in 4 dimensions. So every single point you see in this picture corresponds to a 4-dimensional Fano variety up to QG deformation. So you can think of each of these points as representing a Fano variety. Or equivalently, under mirror symmetry, each of these points is corresponding to a Laurent polynomial or to a quantum period. Okay. Yeah, the period sequence is it's infinite, so you can think of it as an infinite vector. But data science techniques basically said, no, you don't need to look at the infinite vector. Instead, you can collapse this down to just 2 dimensions worth of information. Okay, and so these 2 dimensions worth of information are what's plotted or encoded by the X and Y axis. So each of these points represents a Fano variety, and their position in the X and Y axis is determined from data science techniques, in this case PCA, and it encodes the infinite amount of rich geometric information that's in the quantum period, in the period sequence. And then what we've done is we've colored them, and we've colored them with a gradient that basically depends on the curvature of the Fano variety. Okay, this is in essence a measure of least curved to most curved. Okay, and there's no reason you'd expect this from the theory, but what you see is this beautiful increase in curvature as you move from the right-hand side of this picture to the left-hand side of this picture. Why is it there? No idea. The general theory says, okay, this isn't mad, but nobody would have actually conjectured this would be the case. How we're ever going to prove this, I don't know, but it's incredible. It's showing some real structure in this classification of Fano varieties. And I'm sure, to me now, I'm used to this picture, but this is the first time you've seen it. I mean, you can't ignore this structure, okay? And then at the same time, you can't ignore this sort of cloud of stuff around. So what's going on there? Unfortunately, I don't have a 4-dimensional picture to show you, but I do have I don't have the 4-dimensional Fanos picture to show you, but I do have the equivalent picture for 3-dimensional Fano varieties. And actually, it's exactly the same. It seems to be dimension invariant. So rather than projecting into just 2 dimensions, what we've done is preserved a little bit of extra information about the period sequence. And what we find is there's this triangular wedge here. And most of the Fano varieties live on this triangular wedge. And it really is just a flat 2-dimensional thing. And then there's a little orb around, ignore these red points, they don't mean anything. There's a little orb around the triangular web of Fano varieties. And jumping to the equivalent picture for 4-dimensional Fano varieties, the triangular wedge consists of those Fano varieties that have Fano index 1. So Fano index is a property of Fano varieties. It's Fano index 1 varieties are the key ones to classify, and they all live on this little 2-dimensional wedge. And then the orb of points that are sort of sitting off this sort of artifact of projection, these are the higher Fano index varieties. In some sense, the less interesting ones for us. What we're very interested in is the Fano index 1s that all just sit on a little 2-dimensional wedge. Why? Literally no idea. No idea whatsoever. I wouldn't have predicted that in a million years. And then just conclude with this this picture. So we've sort of zoomed in a bit on the previous pictures we've seen, and we've colored them slightly differently. So here we've not taken the whole classification, we've just taken a sub-classification, and we've colored the Fano varieties by having what's called the same Hilbert series. So a Hilbert series is a much more refined measure of curvature. You can think of the curvature as being the very crude thing to measure, and the Hilbert series is a much more refined, again, infinite series of integers that describe or encode the curvature. And sort of expressed geometrically, each of these colored blocks represents a Hilbert scheme, and each point within the block, well, it represents the deformation of family of Fano varieties, so it represents a component of the Hilbert scheme. And again, there's zero reason why you've expected it. You find that the Hilbert schemes are falling in these linear patterns in this projection. Absolutely zero reason why you should have expected this. And the most wonderful thing is, all of this is sitting inside this triangular wedge. And so you can take one of these little linear features, this Hilbert scheme, and you can look for obviously missing Fano varieties, points that look like should be there, but they're not. Then you can go away and you can find that that Fano variety exists. So again, I zero idea how to prove this at the moment. I think it's going to take decades of work, but this fantastic rich structure that's been exposed by data science is really helping guide us to how to classify and understand the landscape of Fano varieties in higher dimensions. Okay, thanks very much.
Thank you, Alexander, for this fascinating talk. So questions now?
Al, can I pose a question?
Hey, Al, yeah.
Hey, Al, this you were sort of apologetic. This was absolutely fantastic. I love it. It's insane.
It is insane.
Could I pose something a little concrete? There's sort of an obvious question, and it's sort of, I'll take you back a few slides where you had the color changing as you move from right to left. And so you told us, you gave this, there are two parameters here, and you didn't say explicitly what they were. You even referred to, I think, PCA somewhere, and I don't know what that means. Right. But there's something encoding in these two parameters, and clearly it looks awfully like the curvature is somehow a function of the x coordinate. This is what you're saying. And,
absolutely.
And I'm thinking what you're saying here is that while the x coordinate is somehow hard to describe, whatever it is, the curvature is in there somewhere, and that's something for future researchers to find out.
Yeah, exactly. So, what are these axes? Where have they come from? What we did was we just took those period sequences, infinite dimensional vectors of integers, okay? And we fed them into this data science technique called principal component analysis, which you might have heard of. And essentially what it tries to do is it tries to
the acronym, but yes.
Yeah, a good basis that characterizes most of the data. Yeah. And what principal component analysis says is essentially all of the features of that period sequence is contained in 2 dimensions. And the contribution from the infinite rest of the stuff is very minor. Okay. And I've got no idea what the actual projection is that principal component analysis is choosing. And I have no idea what the geometric interpretation is, but it boils down those infinite period sequences to just 2 numbers.
And so crucially, you don't know it's enough to truncate to the first 10,000.
Oh, no, for sure. That's not true. I mean, a little bit of sort of theoretical analysis of the period sequence. There's sort of, it's a bit like a Hilbert series in some sense. There's sort of chaotic stuff at the beginning.
Right.
And then it settles down to more asymptotic growth. And it seems to be that, principal component analysis is somehow picking up the asymptotic growth of it. And that's enough.
That's cool.
Have you checked if any of this is related to vibration structures?
No, I'm afraid not. It's a great idea. Yeah, absolutely. I mean, and we should make more of the classical period as well. Absolutely.
Yeah, I'm asking this because we've seen. I mean, there is a classical plot of Hodge numbers for Calabi of 3 folds in the Kreutzfeldt-Parke list, and you have a similar problem. Why a triangle and why a certain distribution? And it turned out all this to be related to K3 vibrations, which are also elliptic vibrations, and this kind of structure.
Yeah, no, absolutely. I'm afraid this is all just stuff we discovered over the summer when we had nothing else to do because nobody can work during the pandemic. So I'm afraid, but no, absolutely. There's so much sort of theoretical. I don't want to say so much maths because data science is maths, right? But there's so much theoretical maths to do here to try and understand it. It's incredibly rich. Yeah, absolutely.
Pierre Deschamps had a question.
Yeah, I was actually going to ask exactly the same or say exactly the same. Fantastic talk, Al, and really interesting and crazy results. And I was also going to ask about the geometric interpretation of the principal components, but you've answered that already. Thank you.
Cheers.
Yes, Yang. Yeah.
Hi, Al. Thanks for that fantastic talk. It's really, really beautiful overview of the stuff. So actually, even though you and I work on machine learning algebraic geometry together, my question is actually something slightly different, which I think Ali would appreciate. The coefficients of your Newton polynomial.
I've already asked this question about 10 years ago.
Oh, you did? Okay.
Go ahead.
So what is the answer?
I'm afraid the answer is going to be no, but go ahead.
Oh, okay, that's good. That's it.
Yeah, so, okay, go on, Yang, ask away.
Okay, no, I was just saying that these in the Dimer model interpretation that we've been working on with Hanan, the school of Hanani, and then which Ali and Alistair also working from the mathematical point of view. For every one of these toric diagrams, we associate a perfect matching in terms of GLSM fields, and for the example you've given looks exactly like the one that we have. So I guess that was the question that Ali was asking 10 years ago.
Yeah, no, it's true, and it is tempting to connect them to Dimer models. And in the 2-dimensional case, you really can make connections to Dimer models. You've got to be slightly cautious. Of course, I lied slightly throughout the whole talk. And it's not just one Laurent polynomial that you have, but a whole family of Laurent polynomials corresponding to deformations, toric deformations of your variety. And so although the pictures I've drawn have always been reflexive polytopes, and so like you see in the diamond models, you know, actually the choice of a reflexive polytope is kind of meaningless from this viewpoint. And really, you know, these are polytopes, or families of polytopes that can have arbitrarily many points inside them. So they don't really fit very well into the diamond model interpretation.
Right, but the dimer model works for arbitrary.
Yes,
right, absolutely.
The number of interior lattice points isn't the problem. So the thing that Yang is excited about are the binomial coefficients going around the boundary.
Yeah, I suppose I didn't quite say it. The thing is that there's points assigned to there's coefficients assigned to the interior too, and these are important. Okay. So, I mean, you're right. And in fact, it's a theorem. We can prove that you always end up with binomial coefficients on the boundary. Okay. But then there's also values ascribed to the points inside. You know, I'm not saying that there isn't a connection. Okay, perhaps more I'm saying we don't know what the connection is. Okay.
It's interesting because it's like, if so, these integers come from completely two different stories.
I mean, one of the really interesting things for us is, because there's so much study being done of the two-dimensional polytopes in this sort of context, you know, the connections with quivers and cluster algebras, all this sort of stuff. And all of this works really well in the two-dimensional case, and none of this theory is developed in higher dimensions. But the way we put these coefficients on it's dimension agnostic. It doesn't care what dimension we're working with. I mean, it does get more subtle, right? There is a sort of complexity shift from 2 to higher dimensions, which essentially boils down to the fact that you have unique Minkowski factorization of a line, but you don't have unique Minkowski factorization of 2 or higher dimensional polytopes. Okay, essentially that's where this complexity shift comes from, and maybe explains why there are these links in the two-dimensional case, but not in higher dimensions.
But we're interesting. I think like Vafa and Rak and Sebastian have worked on these brick models where these numbers are computed. I forget what they are.
I mean, there's a paper come out quite recently. I say recently, I think like 2009, by 2 people in Japan, Akihiro Higashitani and I've forgotten his name, but you know, they really do. Was that, sorry, Ali?
Yusuke Nakajima?
Quite possibly, I think that's right.
Deformations of diamond models.
Yeah, exactly. And they've really started to build this link, absolutely.
Thank you. Good to see you, Ali.
Likewise, mate.
I have a slightly different question. So what you studied was quantum periods, right? And series where the coefficients are counting curves, Gromov with an invariance.
Right.
Would you expect if you were counting something else like divisors? So you would have effective divisor or something. You would have a series with that. Would you expect that? I mean, that would carry a lot of geometric information as well.
I mean, here we've linked the quantum period to the Hilbert series. So yeah, for sure. I mean,
that would be
yeah. I mean, it wouldn't surprise me at all.
Okay, well, it's a very, very general question. So
yeah, I mean, when I say it wouldn't surprise me, what I mean is it would really astonish me and surprise me. But yeah, probably it will.
Yeah. Okay. Any other questions for Alexander? Yes, if not, this is the end of the first part for today. So we resume again in 1 hour.
Thank you, Andre, for chairing this session.
Thank you to all the speakers.